Very, very pleased to be part of this story. It's a small spacecraft, but it's an enormous story. In a morning like this, you really feel it. Here's the ocean, it's the sunrise, the yellows, and it gives way to the blue sky. And then beyond that is space. And we're just part of this whole enormous thing, the cosmos. Carl Sagan talked about this dream of sailing through space pushed by photons, the physics of light.
Well, there's a just tremendously exciting prospect called solar sailing, which travels on the radiation and particles that come out of the sun. See, it's a whole new kind of idea.
So this dream of Carl Sagan's, Bruce Murray, and Lou Friedman, the founders of the Planetary Society, is going to be realized at last.
3, 2, 1.
We got 50,000 people around the world who just thought this was an inspirational thing to invest in. So together, we built a spacecraft, a real spacecraft. And we're doing this just to advance space science and exploration because we want to know more about the cosmos and our place within it. We want to know more about where we fit in.
Everyone, I want to thank you all for your support.
I mean, I think Carl Sagan would be very proud of this effort.
Welcome to a celebration that many of you have made possible. It was 1 year ago, actually 1 year and about 16 hours, if I figured it out correctly, that many of us watched a SpaceX Falcon Heavy liftoff with more than 20 payloads on board. One of those payloads was a tiny spacecraft called LightSail 2. Now, after a full revolution around the sun and thousands of its own orbits, we're ready for a transition in this mission that has already accomplished so much. I'm Mat Kaplan of the Planetary Society, host of our weekly podcast and public radio series, Planetary Radio. Over the next hour or maybe a little bit more, we will review the mission of LightSail 2. We'll hear about the long road to its success. We'll share a handful of the stunning images that it has captured, and we'll answer some of your questions. We'll close with a toast to this mission and the tens of thousands of men and women behind it. So be ready to raise a glass with us. That toast will be delivered by the Chief Executive Officer of the Planetary Society, Bill Nye. We're going to hear from Bill in a moment. But first, I want to introduce to you the other people on your screen. Jennifer Vaughn is the Society's Chief Operating Officer. She has been a passionate advocate for this project from its earliest days and had much to do with ensuring its success. Bruce Betts is Chief Scientist for the Planetary Society, and that means he has to juggle a lot of projects, but it's his service as LightSail Program Manager, he really does juggle, that probably has dominated his professional life over the last few years. Working closely with Bruce, is the LightSail project manager, Dave Spencer. Dave has spent decades working on and guiding some of NASA's most exciting missions across the solar system. Lately, he's been at his alma mater, Purdue University, serving as associate professor of aeronautics and astronautics. He's also the founder and director of the Spaceflight Projects Lab at Purdue. And in a few minutes, though, we'll ask Dave about his brand new job, one that has returned him to the Jet Propulsion Lab, not far from Planetary Society headquarters in Pasadena, California. Bill, we now have over 500 people online. The numbers are still going up. Most of those folks who've joined us for this celebration are either members of the Planetary Society or have provided other support for LightSail. Do you have a message for them?
Thank you. That's my message. Thank you so much. Thank you so much for your support. This dream goes back centuries, and then for us, decades. And so we have realized it because of the support of 50,000 people around the world who thought this was a worthy use of our intellect and treasure, and support our mission to advance space science, to advance exploration, so that we can know more about the cosmos and our place within it. It's a real mission, and you all have reified it, have made it happen. So thank you so much. You know, I think all the time, you guys, everybody understand, you may have heard this story often enough from me, but I am a mechanical engineer because I like bicycles, I like airplanes. I finished my mechanical engineering requirements, and for fun, I took an astronomy course from Carl Sagan when I was in college. And the guy changed my life. I was in class when he talked about a solar sail mission to Comet Halley, and the orbital mechanician, the guy doing the computations for how you would get into Earth orbit, make the orbit retrograde by going over the top of the Earth and then catch up with Comet Halley, was Lou Friedman, one of our founders, along with Bruce Murray, who was the head of the Jet Propulsion Lab at that time. And so it goes back to those days where people had this romantic idea of using a spacecraft that didn't need any fuel to catch up with a comet whose tail is generated by photons from the sun, not the solar wind, not particles from the sun, but you would get propulsion rather, not from the solar wind, but from photons. And this goes back really to Johann Kepler in 1607, saw the same comet, Comet Halley, before Edmund Halley had made a prediction about when it would return, and Johann Kepler reasoned that whatever's producing these tails could one day provide propulsion like wind provides propulsion for ships on the sea. So it's romantic, but not only that, it's practical. Not only that, it's astrophysics, it's pure science, it's pure physics, it's pure understanding of energy and motion in the universe. And so to realize this is really something. And then, you know, we are an international organization, and we worked closely with people from the Japanese Aerospace Exploration Agency when they produced manufactured a solar sail that worked in deep space, but could not be steered fast enough to do something like we're doing in low Earth orbit. And so with the international community, and your help, we built this spacecraft and shown that it can, and we have shown that it can be done. You can steer a solar sail spacecraft in Earth orbit fast enough to increase its orbital energy. And one of the spectacular things about today, the 1 year, would you say, Matt, 1 year and 16-hour anniversary
Yeah,
of the launch. Of the launch is that we have not burned up. The spacecraft is still flying, and program manager Dave Spencer and then project manager Bruce Betts will talk about this in the next few minutes, that we have been able to maneuver and keep very nearly at the same orbital altitude we had a year ago. We barely lost 10 kilometers of altitude, which is really amazing. And so It's thanks to you all. And I'll just point out that if you did this, and I guess Dave will speak to this, if you did this at a regular space agency, you know, when people think of space exploration, they think about NASA, the world's largest space agency, 3 times bigger than all the other ones. You would expect to spend 20 times what we've spent, 120, $150 million US. But we spent, thanks to you all, $7 million over the course of our whole program, a whole LightSail program, LightSail 1 and 2. And the thing that also for me is so gratifying, you know, it is said, and nobody's really been around to dispute this, it is said that our own Bruce Murray, one of the founders of the society, was in these meetings early on in space or planetary exploration in the 1960s. And he apparently, by all accounts, was the guy pounding his spiritual fist on the table saying, you guys, we got to have cameras on the spacecraft that's going to Mars, the Mariner spacecraft, which was a repurposed Ranger spacecraft, which went to the moon. We're going to have cameras. And people say, oh, no, that's a publicity thing. You know, there's not any real science. There's nothing to be learned by putting cameras on a spacecraft. That's just for PR. And he insisted, no, we can learn a lot with cameras. Everyone, can you imagine a space program without pictures? Who would even care? I mean, who would even know it happened? And so along with all the, I think, remarkable engineering accomplishments Dave, Bruce, and the team have produced over the last year, well, the last 10 years, especially the last year, are the pictures. You know, with LightSail 1, it was all we could do to get down one really nice picture. But we got a whole bunch of pictures, but one really nice one. Well, now the pictures that have come down from LightSail 2, to me, well, they choke me up. It's just spectacular. And so with that said, and with me going on and on about the team and all the great things that have happened, this has been a long road. It's been a long road to get from the inception of the society, the dreams of the founders, the failures of a spacecraft, a couple spacecraft called Cosmos 1, and now the success of LightSail 1, and now the spectacular success of LightSail 2 has been a long road. And you know, I'm the CEO. Once in a while, I'm asked to sign something or go on camera and say something. Once in a while, I make a decision, but the place is run by our operating officer, our chief operating officer, Jennifer Vaughn, and she's here on camera with you. So Jen, I'd like to hand it to you for you to talk about the operations and what you did with all the people watching today to bring this mission to fruition.
Thank you, Bill. Everything you just said just hit it right on the head. And it has been such a journey. And one of the things I always like to just take a moment to reflect on is that it's really been your journey. It's sure we get up in the morning and we try to think about how we're going to best include you in space exploration, but it's you that make it happen. The Planetary Society is your organization. So this journey for all of us really began at our founding, when early on, when the founders were trying to figure out, what is this organization really going to do? Is it just PR? So going back to the same idea about images, is it just about trying to get more people interested in space, or are we really going to do things? And the founders came down strongly that we want to facilitate advances in space exploration, particularly planetary exploration. So with that, they started a program to develop science and technology projects that began in 1981. We were founded in 1980. So it's just stunning to me how quickly they moved on this idea and made it into a reality. And those first projects, they were modest. They were the things that we could take on at the time. We could pay for some travel to get people to go to a conference. We could fund a small piece of hardware development and advance a larger project. And over time, we did more and more. So looking back on our history, in the 1990s, we were getting involved with direct space missions and doing activities like our Mars microphone that flew on the failed Mars polar lander, but still it flew. It made it onto a NASA mission. The NASA mission didn't survive, but our payload was on it. And that was a Planetary Society member-funded payload. So little by little, step by step, we took bigger moves. We made bigger moves into the space frontier and brought all of the public along with us as we did this. So as we moved forward into the Cosmos 1 years, that was an opportunity where we could make a small investment in a larger mission project. So we were going to invest in the sail part of the mission. When that failed, we had the opportunity to say, well, now what? And we said, let's do the whole mission. Let's do the whole mission completely funded by the public. And that, in addition to all the technical work that was happening, was no doubt very challenging, but the good kind of challenging, the challenging that wakes you up and gets you excited to get to work because you know you can do it. You just have to work. So stepping back now and seeing the success, it's that moment to say, this is what can happen when individuals come together and rally around a belief, an idea, something that we're all passionate about, and then work in one direction to make something happen. This is what happened. And so where I stand right now is I'm excited about what could happen next. And while we can't answer the exact answer to, well, what is next? We know that we have this history that has grown and grown and grown in capacity. And I have deep, deep hope that public involvement in space is just going to continue to grow into the decades ahead of us. So as Bill said, thank you, thank you, thank you to the 50,000 people who made this happen. I like to say, imagine what 100,000 people could do. Imagine what 1 million people could do.
I'd like to see that. Well, maybe we'll find out. Put the word out, folks. And if you're not a member of the Planetary Society, but you're loving all this that you're hearing and what we're up to, planetary.org/membership is the place to visit to learn more. We don't want to make this sound like an epitaph. As somebody in a baseball cap in a dugout once said, it ain't over till it's over. We're not done. This is a marking of a change of phase, a change, a transition. What are we transitioning to? And Bill, did you have something else you wanted to say?
I just want to say, everybody, for those of you who for some reason are not members, just if you like birds, you join the Audubon. If you like the environment, you might support the Sierra Club. If you like space, the Planetary Society is here for you. This is what we do. We advocate for space exploration in governments. We educate people through with our remarkable journalists and our website and our publications, our magazine. And then we innovate. We do things like LightSail. So if you like space, the Planetary Society is for you. Back to you, Matt.
Well, what about that question? What are we marking here? It is a first anniversary, but it's also a transition. And I don't know, Jennifer or Bruce, either one of you can tackle that. Where are we headed?
Yeah, Bruce, do you want to take that?
Sure, I'll take that. So we're formally ending the primary mission phase, which we took as a year in orbit. And we're beginning our extended mission phase, which is a continuation where we're going to, both I and Dave are going to talk about this. We're doing stuff, we're learning stuff, we're still up there, we're still solar sailing, and we are trying to get the most out of this mission in the extended mission phase, and we'll both be talking more about that.
Well, let's go right on with that, with you, Bruce, and Dave Spencer. Where are we? Where's the spacecraft? What's the status? What kind of shape is it in? I know you've got some stuff to show us.
Do you see my pretty slide?
I do.
Excellent. Let's see, get so I can see my pretty slide.
It is pretty.
Isn't it pretty? We're gonna look at images in a little bit. We're gonna talk about the status of the mission, the engineering, but I can't help myself showing images up there. So let me get Windows out of my way so I can see what's going on here. And so I will be talking. I'm the program manager. Dave Spencer will be talking. He's project manager of this mission. LightSail 1 and 2 have been important notes developed and flown by your independent international nonprofit organization, almost without precedent, certainly for this kind of mission. Supported solely, as I think we've mentioned, by more than 50,000 donations. That's you who's watching right now. So first I want to start with a big thank you. Thank you. All right, let's talk about what we've achieved in our primary mission. Again, we'll come back to these, but you can enjoy the 5 images from each of the sails deploying each of the 2 directions. We've got cameras, we'll talk about that and show lots of pretty pictures in a little bit. So our overarching goal technologically was to demonstrate controlled CubeSat solar sail propulsion. As Dave's going to talk about, we've done that. We're up, we're controlling a sail in Earth orbit, we're changing its orientation twice per orbit. We also wanted, we're the Planetary Society, so we want to engage people. Sorry, got my bullets backwards, but let's throw up the other bullet. Excite and engage the public. And I think that's what we've done, what we've seen in the outpouring of support for this mission. But we also wanted to raise the profile of this sort of obscure propulsion technology, which holds a lot of promise for the future in planetary exploration. And we've done that both in the public and the technical communities. We have done that in part by sharing the results of the mission. So we've got a whole group of people on staff who work to get the information out to you and to the public. We have submitted and presented several papers at technology conferences and done presentations publicly. We will continue that. We've got a major paper that Dave has led that has just been accepted in special solar sailing issue, where we get to be the one who actually is flying a solar sail mission with a paper in that article, in that journal, sorry. Advances in Space Research. So let us review where we are. What is the current status? By the way, pretty picture, we'll come back to it, but that's the Nile River and the Red Sea, you're right. We're still solar sailing, lest we forget. We're actually up there solar sailing around 700 kilometers altitude. We're still learning from what we're doing. We're trying new and different things to optimize the sail control. We're sharing what we learn, as I just mentioned. We're still working to inspire and excite. And I think pictures like this, results like we've got, are inspiring and exciting. We are leading into future solar sail missions. For one, the NEA Scout mission from NASA, which will launch in the next couple of years, Near Earth Asteroid Scout. We have an agreement with NASA where we share information with them, and they'll be off to a near Earth asteroid to study that. And we're taking we're taking engineering pictures. The primary purpose of the cameras functionally was to verify the deployment, continue to monitor the sails and learn the status of the spacecraft. But of course, we're the Planetary Society. We want to take pretty pictures. We want to get people excited about space. So we're continuing to do that. And while we're doing all this, we are gradually descending due to atmospheric drag. So we've got the, and Dave will discuss how we do this, but we've got the solar photons that are trying to increase our orbital altitude. But all the time, we've got a little tiny low mass spacecraft and a really big sail. And so even at a little bit of atmosphere up at 720 kilometers altitude, or 700-ish, is going to cause atmospheric drag, and eventually will drag us down into the atmosphere, but we've got at least many, many months left. I want to mention the current LightSail 2 operations team. The list of people and organizations who have been involved in creating, developing, designing, testing is huge, and I'm not going to go into that now. You can find it on our website at sail.planetary.org, but this is the core operations team, and it's part of our efficiency in doing a mission much cheaper, is we have a small but very efficient, very capable, great team. And Dave Spencer, you've met, you'll be hearing from Purdue and now JPL, but still an adjunct professor at Purdue. Me from the Planetary Society. John Bellardo, who's heading our software development. He also oversees all the ground station. He's at Cal Poly San Luis Obispo. Alex Diaz at Ecliptic Enterprise, who took over a lot of the integration and test, and Alex is still involved. Barbara Plant from Boreal Space doing a lot of the attitude control system work. Justin Mansell, another important thing that's happened in LightSail, not by coincidence, is involving students. And Justin is one of Dave's PhD students at Purdue, and he's been critical to analyzing the orbit and many other aspects of the mission. Liam Mages is currently as an undergraduate at Cal Poly, overseen by John Bellardo. We've had a number of undergraduates involved as well. So for you looking for more information when you come out of this call and you go, I still want to know more, I love this so much, go to sail.planetary.org, and if I've still got my little pseudo laser pointer, you can see that blue box. That'll take you to the latest mission updates by our star journalist, Jason Davis, who is doing updates periodically on the mission. You can also find pretty pictures there. You can follow the link just below that, which will take you to this page on the right, planetary.org/mission control. You can see where LightSail is right now. This is not a live image. LightSail is actually coming over overhead in Baja California area in a little bit. It's over the Pacific right now. And you can get key information about the spacecraft as well as look at its orbit and evolution. And then there's planetary.org/radio. You can see Matt and I have a good relationship built up trust over 17, 18 years doing Planetary Radio. We just did an episode a week and a half ago where you can learn more about the mission. All right, we have actually achieved some really interesting awards in this process, and the winner is us, LightSail 2. Time Magazine named us as one of the 100 best inventions of 2019, sailing on sunlight. Popular Science named us one of the most impressive aerospace inventions of 2019. We were the grand award winner in the category, the aerospace type category that we were in. And we even sort of made a question on Jeopardy in 2019. This heavy SpaceX rocket launches solar sail testing for space travel powered only by sunlight. That's us.
What is LightSail?
No, what is LightSail 2? Actually, it's what is the Falcon Heavy, but whatever.
He gets enough credit. All
right, let me finish off this part. I'll come back and guide you on a world tour with images in a little bit, but LightSail 2 first. This first one's the main one we were driving after technologically. The first small spacecraft, in this case a CubeSat, propelled by sunlight alone. This demonstrating not just that you could do this in Earth orbit, but the viability of solar sail propulsion for CubeSats. CubeSats, which are by definition small, they're used by universities and agencies in Earth orbit, but very little out beyond the Earth. And part of it is a limitation in propulsion. Well, if you don't have to carry fuel and you can shove a boxing ring size sail into a loaf of bread size spacecraft and operate it successfully, well, that might open up some possibilities. Also, the first crowdfunded, that's you, thank you, spacecraft to test a new method of propulsion, and the first controlled solar sail flight in Earth orbit, and little known fact, highest performing in terms of acceleration solar sail flown to date. That's basically a comparison with Icaros from the Japanese Space Agency, which although it had a bigger sail, was much more massive, and the acceleration is tied to area over mass. Let's go on to Dave, and I'll just throw up the slide and immediately throw you into it. Dave Spencer, Project Manager.
Okay, thanks, Bruce. So just to remind everyone, this is how we actually do solar sailing in Earth orbit. Basically, we're putting the sail face on to the sun direction when the sailcraft is moving away from the sun. Then we do a 90-degree turn and turn the spacecraft edge onto the sun as it's moving towards the sun and that portion of its orbit. So we make two 90-degree rotations every orbit. An orbit is about an hour and a half. I think we started out with a 100-minute orbit period, and that's come down just slightly. And so the effect of doing this solar sail control strategy is to increase the apogee of the orbit. The far part in the orbit, we're basically thrusting during the period where we're moving away from the sun and eliminating that solar pressure thrust when we're moving towards the sun. That has the effect of increasing the eccentricity, making the orbit more eccentric, more oblong, I guess. But we're also battling atmospheric drag, and so over time, the average orbit altitude is decreasing. You can go on to the next slide, Bruce.
Sorry, working on it.
While you're working on it, you guys, oh good, okay. I just want to say I got I have the app, you know, it's big fun to watch where the spacecraft is, fighting the reflection there.
I'm in San Diego. I got to run outside for a minute and look up. I'll be right back.
Matt, it's daylight.
It's hard to see in the daytime, but boy, when you see it at night, it's really something. Thank you, guys. Carry on.
All right, and today we're celebrating 1 year from launch, and I remember that night well, but I can't believe it's only been a year. It seems like we've been operating the spacecraft for much longer than that. But you know, LightSail was deployed into orbit by a small spacecraft that was built by students at Georgia Tech, Prox-1. We actually, after launch, the whole flight team traveled out to Cal Poly San Luis Obispo and awaited that initial radio signal from the spacecraft, and it occurred within seconds of the earliest possible time that we could receive that signal from LightSail 2 after it was deployed into orbit from Prox-1. And then the race began to try to get the spacecraft well situated on orbit so that we could deploy the solar sail. And I'm going to talk about that some more in detail. But it was July 23rd that we had the big solar sail deployment event, and we've been operating the spacecraft ever since then. The team meets every evening, 5 o'clock Eastern time, 2 o'clock Pacific time. We have our daily tag up, and we're evaluating the downlink telemetry from the spacecraft and assessing health and status. And as Bruce said, we're still trying to make improvements in terms of our solar sailing control strategies. So go ahead to the next one, Bruce. So we had about a 2.5 week period after we received our first signal from the spacecraft, and we checked out the health and status of the spacecraft. Everything looked good. But the real crux of the matter was, can we control the orientation of the spacecraft relative to the sun? You need to know first what the orientation of the spacecraft is based on the sensors that are on board the spacecraft, and then the algorithms, the software that controls the spacecraft, has to work properly to orient the spacecraft. LightSail 1, which we flew back in 2015, didn't have attitude control capability. It couldn't control its orientation relative to the sun. That was a test of sail deployment. LightSail 2, we want to control this solar sail. We want to use the thrust from solar pressure to change the orbit. So we had to be able to control the orientation of the spacecraft. And this is a plot. It took us, 2.5, 3 weeks after the initial radio signal from the spacecraft to get to the point where we could do this demonstration that we could actively control the orientation of the spacecraft. And the red line here shows the angle between the long axis of the spacecraft and the sun that was desired. That's the 90-degree on-off turns that I was talking about. And the black line shows what the actual performance was. And we worked really hard to get to this point, and I couldn't have been happier once we actually got this actual in-flight result. So this told us, hey, we're ready to actually deploy the sail. If you go on to the next slide. So once we deploy the sail, it's like the figure skater, extending her arms. That slows down the rotation of the vehicle. It changes the inertia properties of the vehicle, and so it was actually much harder to control the vehicle once we got the sail deployed. But this is a really good illustration of what our on-off control looks like with the sail deployed. And ideally we'd be right on top of the red line. You can see that some of the turns are done very well. Some of the turns, aren't done as well, and that's just kind of, we've got a large flexible structure up there. But this actually matches up really well with what our modeling and simulations pre-launch showed the attitude orientation of the sailcraft should be during operations. And this is a couple of representative orbits from August and September of last year. And so with this sail control strategy, we were able to raise orbit apogee by 9 kilometers over the first 30 days of sailing. But there is a long-term decrease in the average orbit altitude due to atmospheric drag. So we started off at an altitude of about 717 kilometers on average. In the almost a year that we've been solar sailing, we've decreased by just about 10 kilometers, which is really amazing. Some predictions showed that we would actually be deorbited by now, but with our sail control strategy, we've been able to fight atmospheric drag and hang in there. And who knows? It could be another year or so before we actually complete the extended mission and deorbit. You go on to the next slide, Bruce. This plot shows uncontrolled solar sailing shown as black bars versus controlled solar sailing shown as blue bars. And basically what we're seeing is that when we're controlling the solar sail in our on-off sail control strategy, on average, we're losing about 20 meters per day of altitude. But if we were uncontrolled, we lose about 34 meters per day. So that 14 meters per day is basically what effect we're having in terms of sail control, using the solar pressure from the sun to fight atmospheric drag. We have had days where we've increased the average orbit altitude, increased the orbital energy by up to 7.5 meters per day. The atmosphere is quite variable due to the changes in the solar cycle and how much solar input is going into the atmosphere. So it does change, and it's difficult to model, but we feel very happy with what we've been able to do in terms of the attitude control and the resulting orbit history. Next slide, Bruce. As Bruce mentioned, we've taken some stunning images, and he's going to show you just great images of Earth. I found this image to be really revealing. This was an image that we actually learned about an anomaly that we had on board the spacecraft that was previously not diagnosed. And if you look at the shadows of the solar panels here, we have 4 different solar panels that deployed. All of them were supposed to deploy to the same angle. You can see the one on the lower left in this image is not at the same angle as the other 2 that are shown here. And we had some insights into this beforehand because the magnetometers that were mounted, one of them on that solar panel, one on the solar panel opposite, they were giving very different readings, and we couldn't resolve that discrepancy until we saw this image. Also, Bruce, if you can point out on the lower right part of the image with the cursor, there's what we believe pretty strongly is a track boom, one of the 4 booms that actually pulled the sail out from its storage compartment and is intended to hold the sail in its rigid, flat configuration. Apparently it's not in the right location, and that indicates that this track boom, which is made of 2 pieces of alloy stainless steel that are welded together at the center, apparently this boom buckled at some point, whether it was during deployment or after deployment, we don't know. But you can also see a gap in the sail there that presumably results from the boom being not in its rigid orientation. So this is an unexpected anomaly for the spacecraft, and undoubtedly the spacecraft is not as flat and planar as it would be if that boom was in its proper orientation. But nevertheless, we've been able to continue on with our mission operations. But just an indication of what a value having imagers on cameras on board provided the overall mission. Next slide.
Any more slides? That's it for now. We'll get to images in a second or two, but I bet we've got some questions. I know I have some. Bill, Jennifer, if you want to jump in, feel free. But a lot of people are already asking, how long have we got? How much longer will LightSail 2 be able to maintain its orbit before it returns to where it came from?
Yeah, it's a good question, Matt, and it's a difficult question to answer because a lot of it depends on how effective we are in solar sailing. I ran a simulation earlier today, one of my students did, that started with the initial conditions from sail deployment day, and we put the sail at a 60-degree orientation relative to the atmospheric drag direction, and that gave us a deorbit in November of 2020. Now, we're clearly, based on our decay rate, going to go well beyond that with our sail control strategy. So, your guess is as good as mine, and the decay rate is going to increase, but I would guess it's going to be, sometime next year, and I'm guessing the second half of next year.
Wow. And so, Dave, if I may, this orientation that happens with every orbit, this the double twist, is automated, right?
Right.
It started out you guys thinking deep thoughts about when to do it, but now it's you've figured out just when to give it a jolt, right?
Well, we're doing that, yeah, twice in orbit, and that's pretty much been unchanged. But the real trick has been we've got this little momentum wheel on board the spacecraft that's used to control the orientation of the spacecraft, along with some torque rods. But the momentum wheel is doing most of the work, and that momentum wheel builds up speed to the point where it saturates. It gets to its speed limit, and then we have to despin the spacecraft and spin down that wheel. And being able to manage that process has been the real challenge that we've been, really fighting through this whole past 11 plus months.
Oh, and I'll just let me say, let me just add for the listeners, the viewers, the word momentum wheel, it's the same as a gyroscope, but by tradition now, a gyroscope refers to something used for navigation, and a momentum wheel is used for things like that, things like this.
Yeah, that's right. So, we basically the sail control strategy has stayed unchanged, but we've made a number of changes to our momentum management strategies, and we're still working with that, trying to improve things.
I just wanted to make.
Oh, sorry.
I just wanted to make one comment on the trying to predict this. The other thing that makes predicting when we'll come back into the atmosphere particularly hard is that the Earth's atmosphere is variable, particularly based upon how much solar activity there is and solar storms that actually cause the Earth's atmosphere to inflate, and you get more drag. It's hard to predict when exactly and how exactly that'll happen. Go ahead, Jennifer.
Bruce read my mind. That was my question.
Can you guys say something about, and maybe this is the time to answer a question that is also coming from a lot of people, was asked in the questions submitted ahead of our live program, and we get asked all the time about LightSail 3. You partially answered this, Jennifer, but in addition to talking about whether there might be another LightSail, I'm hoping that Dave or Bruce can talk about what we're doing to help other teams, particularly the NASA JPL team that's putting together a mission to an asteroid.
Dave, did you want to? Why don't you take that, Dave?
Okay, well, I can address the part about, kind of how we fit in with technology and what we're feeding forward, and then maybe Jen can talk about the LightSail 3. So, where do we fit in terms of solar sailing technology? Bruce mentioned the Icarus mission, which a Japanese mission that deployed a large solar sail that was spin stabilized. It was spun up, and they demonstrated a reorientation of the sail relative to the sun using embedded reflective devices. But the change in that orientation of the Icarus spacecraft with that was less than a degree. It was like 0.3 of a degree. What we're doing is a 90-degree turn twice in orbit. So, we're much more mobile, much more agile than Icarus, and we're the first solar sailing mission that has really demonstrated that level of sail control and actually actively changed its orbit intentionally based upon that sail control. So that's the key technology advancement that we've made as LightSail 2, and we're feeding forward this technology to the near-Earth asteroid Scout mentioned by Bruce earlier, which is actually going to use solar sailing technology to do a science mission at an asteroid. And to me, that's the big payoff. Can we actually use this technology to go do science or go do infrastructure mission, give us early warning of solar storms, for example? Or Lou Friedman and Bruce Murray's great dream, Carl Sagan's great dream is to take a solar sail, have it propel your spacecraft out to the outer solar system, and maybe escape our solar system and go to a nearby star. So solar sailing is one of the few technologies that can actually achieve that objective.
Jennifer, LightSail 3.
Yeah, I'll jump in. Yeah, so we're learning a lot about solar sailing. We've learned a lot about solar sailing, and we're continuing to try to feed forward. But all that said, we're not the Solar Sailing Society. This is not our business. Our business is involving you in space. And so that doesn't preclude future solar sailing activities, but it also means that we're open. We're open, and as always, we're looking for the best ideas that can be kickstarted by people like the Planetary Society, like the members of the Planetary Society. So with that, we are going to continue doing a lot of what we've always done, which is look for great project ideas that need crowdfunding and support and put our money in those directions. But we're going to regularize it now. So we're going to standardize it. We're going to put out an open call for proposals. have it begin every other year, something that is predictable, open to the international community, open to amateurs, professionals, and looking for great project ideas that we believe our members are going to collectively want to advance. And again, that could be a solar sail mission, but it also may not be a solar sail mission.
Okay, Bill.
Well, let me just point out that this is what we do. Another long ongoing project that we support is the Shoemaker NEO grants, Near Earth Object grants, where we support amateur astronomers looking for asteroids. You know, when I was in school, no one had a good idea what happened to the ancient dinosaurs. No one had a very reasonable theory. I mean, they had small brains, and they went, no, that's no good. Anyway, the asteroid impact was discovered in my lifetime while I was out in the workforce paying taxes and among other things. And so I just remind everybody there's a difference between an amateur tennis player and an amateur astronomer. Amateur astronomers contribute to the science of astronomy. And Dr. Betts might speak to this for a moment, but I don't want to hassle the guy. But the thing is that looking for asteroids takes observations. It's amateur astronomers contribute a great deal to what we like to call planetary defense, keeping the Earth from getting hit with an asteroid. And I mention it because this next project that, as Jen said, this call for proposals, speaking roughly, this proposal seeking activity is consistent with what we have done for years at the Planetary Society. And so LightSail 3, an absolute, without question, maybe. But in the meantime, we're going to be looking for the next cool thing. For those of you who've been around for a while with us, the Mars microphone, the Mars balloon, an airplane on Mars, these are all projects that we've supported over the years, and they all lead somewhere. And so I'll just say again, thank you all. Back to you, Matt.
I know none of you will be surprised to hear that we are getting far more questions than we will be able to handle during this webcast, even if we stayed on for another couple of hours. But we are going to get to those questions, as many as we can, and I'll consolidate some of them as best I can. Before we do that, though, maybe the highlight of this program is sharing some of those beautiful images, and we'll get rid of all those titles and graphics that Bruce put over them. So Bruce, show us the gallery.
All right. All right, let me make sure. Can you see it with graphics on it?
Yes.
Moments, seconds.
Some favorite LightSail 2 images.
What a happy, whimsical title. What a happy, whimsical title.
I worked hours on it.
No, this is cool, everybody. Hit it, Bruce.
All right. So starting with sail deployment, we took images to test the camera out before then, but again, you can find all our raw images online. Sorry, got excited. Here you can see 5 in the sequence from the 2 cameras. So we have cameras on 2 opposite solar panels. They are both 180-degree fisheye lenses. The images I'll show you, these are completely uncorrected. Most of them are mostly correct for the distortion, but not completely, because it's quite extreme in any kind of fisheye lens. But we did that so we could see all the sail area with just 2 cameras. And here we see 2 looking in almost opposite directions, the deployment from camera 1 and then the deployment from camera 2. Camera 1's looking off into space, happened to catch the sun at the beautiful centered on the sail. And then camera 2, we were deploying over Baja California so we could control it from Cal Poly San Luis Obispo, which got beautiful shots of Baja. Here you have videos that will get out of sync, but they string together a bunch of our thumbnail images. All of our things are taken with thumbnails first, so we can choose what high resolution to download. And you can see the deployment sequence from the 2 different cameras. Again, they get out of sync, but you can get what's going on. I don't know how well that comes through with all the motion, but we'll take some freeze shots. This is a bigger version, somewhat corrected, of what we saw. This is prior to the end of deployment, and we called this the Batman image because of the cape look to it. You can see in some of these images from camera 1, those things that are at the very bottom and the lower left. Oh wait, I have a cute little pointer. Those are some of the spectra line, the fishing line-like material that was used to hold the panels closed, and it was visible in the camera 1 images after those were burned through to open up the spring-loaded panels. All right, now we're going to take around the world. Well, kind of not just equatorial, but near equatorial, because our orbit is plus 24 latitude and minus 24 latitude, is as far north and south as we go. We get some views obliquely beyond that, but you'll see everything we're seeing is in that region. All right, here I had to come back to the Baja image, cleaned up a little bit. This is also prior to deployment. You'll notice the alloy booms visible here. Once it gets fully deployed, the sail will cover that over. Baja California and Mexico down here. This I put up front as one of the favorites of staff. This is, I know, Jennifer's favorite image of what we've gotten. This shows the north is to the right, and this is India down at the bottom, the west coast of India, the sun reflecting off of the ocean. And then the sail backlit. In fact, that's actually the sun being seen through the sail. And here's the bent boom up here. But we've got this lovely view. Here is the image that Dave showed you of the shadows that gave us the clear insight that that things were flopped over, the floppy panel, to use a technical term. First, let's talk about what's on Earth. This is Australia, north is to the left, and this is much of eastern Australia with north up here, south Adelaide down here. What I did was Dave and his students do very complicated computer modeling to figure out what's going on, and they came up with later analyses to work out the magnetometer issue. I used a little tiny model and a flashlight and confirmed that indeed you can create that with a flopped over roughly 90-degree panel, which turned out to be close to what the magnetometer measurement showed.
Bill, didn't you used to do things like this on the Science Guy show?
Absolutely. You can't beat a physical model. You just can't beat it. And I worked a little bit on radar reflections from military planes, and you just can't beat a model painted bright silver. You just can't do any better. And well, nicely done.
Thank you. And here we've got some more Australia, and you can see now north is kind of at the upper left, but we've got the Bay of Carpentaria here and northeastern tip of Australia here. We'd be seeing New Guinea, but it's under clouds. Here, we're continuing our Australia tour. Now we're on the west coast of Australia. North is at the lower right, and this is Perth is somewhere around here, if you can see my marker. The Southern Ocean down here and the Indian Ocean off here. We now move to South America, and this is north is at the right now, and we've got the northeastern portion of South America is over on the right side of the image.
Dr. Nye.
Sure. So, Bruce, two things. Would you talk about that blue line on the edge of the Earth each time? And the other thing that fascinates me, you know, I'm not a big time software guy, but you all solved a very troubling problem with signal compression, right? And when I look at images like this, I think about the problem you solved. If you don't mind, enlighten us on those.
Enlighten you. Well, we'll start with the first one. That blue line is the Earth's atmosphere. You're looking through the just same reason the sky is blue. You get a lot of blue light scattering when you're looking at the edge. I should mention that it's always deceiving, even in the corrected things, looking at it. It feels like you're looking at a whole hemisphere of the Earth. We're not high enough up, even with a 180-degree view, to be looking at a whole hemisphere. So you're looking at many hundreds of kilometers, but not a whole hemisphere. But you still are at the edges looking through the atmosphere, and that's what the blue is. The compression I'll try to give a short version, but basically we have limited space for the high resolution images to fit into data slots, for lack of a better term, on the cameras. And it turned out that things were getting corrupted and messed up in our high resolution images. We have the thumbnails, but then the high resolution, some of them are corrupted because it ran out of room to shove them in these slots. And part of that is because the sail, with all those wrinkles and crinkles that I know Bill loves to talk about, you create these very complex scenes, so it couldn't compress it and shove it into the slot fast enough. And so what we did is we went to higher compression ratios, and now we get our high resolution images, and they're a little bit more JPEG compressed, but it works. All right, we move on to Africa and the Arabian Peninsula. We've got the Horn of Africa here. North is roughly at top, the Gulf of Aden, and then the Arabian Peninsula is in the upper right.
Beautiful.
That one's just, that one is just the one that gets me. It's amazing.
Yeah, feel free to leap in with oohs and ahs. Here we've got the Caribbean, and you've got the lovely colors of the Turks and Caicos region, so near the Bahamas. This is actually the eastern, I should say north is at the lower right, roughly at the right. This is the eastern tip of Cuba. And this is the island of Hispaniola with the Dominican Republic and Haiti. And here we get this is Libya over here and Egypt over here. And this is one of the few pictures where we were able to get far enough north and not have cloud cover that you could see the Mediterranean. It's right on the edge of our view. So this is the Mediterranean Sea up here. Notice in these, these desert North Africa images, if you look at the sail, it's reflecting the color of the sand and such, and it's kind of cool. And of course, the sun, that big bright thing over there. Now, Western Africa, north, to confuse matters, north is down and to the left, but this is showing countries including Mali and Burkina Faso, and it's got the Niger River is this dark line going down here, and a really cool cloud pattern. Here we have the Central America. It again stretches your brain if you're used to north at the top, north is at the bottom. And so we've got the Yucatan Peninsula of Mexico over here in the lower right of the earth, and then Nicaragua, Honduras, Central America. You can even see some of the Bahamas, some of the Caribbean colors in the water off here. And this is South America. North is at the upper right, and Chile is on the top here. And these are the Andes Mountains with associated, well, the Andes are kind of down here. What I think is neat is the Uyuni salt flats, which are in amongst the clouds. You see this area, and it's this amazing, gigantic salt flat that exists there. And then as you get over, we just kind of lose the forested area on the eastern side of the Andes. Sorry, twitch, and good. Okay, so back to Australia for a moment. I was hunting for the Great Barrier Reef in an image, and our resolution is not good enough to really pull it out a lot, but you can see in this region, you can see the Great Barrier Reef, the different colors going on, and northeastern tip of Australia. We tried taking some pictures at night in the shadow of the Earth, and it's stretching it out. This is India. And you can see 3 of the big cities of India Bengaluru, sorry for the pronunciation, Anantapur, and Chennai is with north kind of at the right here. So this is on the east coast of India, is right about here. And when we look the other direction, we see a nearly full moon appearing over the sail. So again, not designed to take night pictures, but I think they're pretty cool. And now we move on to Dave Spencer's favorite image, and that shows the reds. North is at the right. We're looking at Africa and the Arabian Peninsula. Notice the sail and the cool color in the sail, but this is the Nile River. This is, you can barely see the Mediterranean up at the upper right. The Nile River going down here, the Red Sea, the Arabian Peninsula.
That's the one that's going on my wall.
And this is my favorite picture, which I left for last. Although it's kind of like picking favorite children. I don't really like to answer that, but Matt wanted us to talk favorite pictures. So when pressed, this is my favorite picture. North this time is pretty much at the top. And this is the Himalaya Mountains. And we've got Mount Everest somewhere in this region, Tibet, the brown area up here, India to the left side of the image. And it's pretty. So we have lots more images. You can find them online, sail.planetary.org. We've got more high res that will be great that we're waiting to get down, waiting for the communication passes. You don't need to see backup slides. We'll stop there. Back to you, Matt.
Bravo, you're a good tour guide, Bruce. Around the world in 10 or 15 minutes.
Very good.
We are already at beyond our nominal stop time for this event.
Sorry.
So I hope that that's okay. It's good stuff. But I'm hoping that the four of you can stick around for maybe even beyond where we were talking about, because it is time for us to get to some questions. And I'm going to start with this practical question that came from Kathy Edwards, who says, so proud to be part of this project, wondering if a recording of this webinar will be available. My son is also a backer, but schedule conflict prohibited him from listening in. Why, yes, Kathy, it will be available at Planetary TV, our YouTube channel, and at planetary.org. It might be a couple of days before it's available there, but I promise you that we will post the whole thing there for you, and that'll be fun. So I've been waiting for an hour now to ask this question that came from someone very special. She says, hello, my name is Heidi Jacobs. I am a proud member of the Planetary Society, and I'm 10 years old. I have some questions for you. You folks have answered one of them about LightSail 3, but here's her other question. Can LightSail still sail with one of its booms bent? And I think you've kind of answered that too, but what if one sail had not deployed at all? Dave, do you think we'd still have been as successful or nearly?
It would have been a big problem because the sail would be asymmetric, and solar pressure acting on it would cause a big torque. It would cause the spacecraft to want to rotate. So I feel fortunate that even though we had a boom that's apparently not in its proper configuration, maybe it's buckled, we still have a sail that looks like it's more or less planar, and we're able to control the orientation of that sail, and demonstrably so, because we're getting the data from the spacecraft that tells us what the orientation is of the spacecraft, and so we can verify that we are controlling the sail as expected. So we're fortunate that we're able to control it, but it definitely is an unexpected, we call it an anomaly.
Heidi, thanks so much for your questions, and thank you for your support. It's great to have you on board. Here's another one that came in prior to the start of today's event from Chris Lawan. Sorry about that. Would it be possible to break LightSail to out of Earth orbit? How cool would it be to extend its mission to include a trip to the moon? Bruce, you want to take that first?
Sure, it would be very cool. Wait, was that the only question?
That's it.
No, I'm kidding. Yes, no, we are not able to take it out of Earth orbit. If you were, we're at an orbit where we're still an altitude where we're still dealing with atmospheric drag, and we just don't have the efficiency, nor did we expect to to move out of Earth orbit. If you got placed into a higher orbit, then without the atmospheric drag, then we could move away. If you build a bigger sail with a smaller mass or some combination, you could move out, but we will not be able to.
So if I could jump in with a backup question, why aren't we at a higher altitude to begin with?
Well, to use the oldest space joke in the world, there's no such thing as a free launch, but you want to get it as as close to free as you can. And so we're limited in what we were able to do. And in fact, LightSail 1 was flown as a test mission to a much lower altitude because that's where most of the spacecraft are going. Most of the spacecraft you can hitch a ride on as the so-called secondary payload and either do it free or cheap is to a low, even lower orbit. So we had to wait for the Falcon Heavy launch, and even that, then we had lots of delays, but then it worked beautifully once it launched. So it's just a limit in what launch we could get, and the fact that we wanted to test this technology. It's a technology demonstration, and Earth orbit was sufficient for that. So in the spirit of efficiency and cost savings, that's what we did.
Okay, here is one more question before we get to those that have come in during this webcast. And it is from, I kid you not, Andrew Planet. And it's something that you started to touch on, the eventual ultimate perhaps potential of light sailing. If a light sail reached another star system, would the radiation pressure of that star stop it in its tracks or push it away? Or could this be avoided by tacking into that light as sailboats do? And Andrew says he'll be wearing his light sail cap during our conversation today. Aren't we largely talking about something more than the light of our sun if we're going to get a light sail to another star system in any reasonable amount of time? Dave?
Well, it depends on what you mean by reasonable, but a lot of studies that have looked at accelerating to velocities that could get you out of the solar system and to another solar system in decades or maybe 100 years. You know, it's still a long time. They go in very close to the sun. They dive in close, get a big push from solar pressure close into the sun, and then when you get out around Jupiter, generally the sail is dropped, because the solar pressure out beyond Jupiter is so small that you're not really getting anything that's a significant acceleration at that point. And so the sail is dropped, and then you've got a spacecraft that's flying ballistically or maybe using more traditional propulsion methods. So in that event, you wouldn't have a solar sail when you get to the nearby solar system.
I'm also thinking of Breakthrough Starshot, that project that is looking out perhaps a century to launching tiny light sails driven by gigantic lasers, either on Earth or in Earth orbit, perhaps, and that they're talking about reaching 20% of light speed, 20% of the speed of light. Does that sound even imaginable to you guys, Bruce?
It's theoretically possible. There are innumerable things that stand between here and there, and we are, solar sailing is in its infancy right now, and it's really starting to be productive, and NEOSCOUT will take it to the next step. There's huge potential in our solar system, for example, for solar weather monitoring, but eventually you'll work out. So I don't know, is my profound scientific answer. I don't know if it's realistic, but there certainly are a lot of things that have to happen between here and there.
Bill, I want to go to you to talk about maybe not the practicalities, but maybe the romance of using this technology to reach the stars.
Well, one of the things that I find quite gratifying is this company Starshot, which has proposed, they've run the numbers about putting enormous lasers on the Earth's surface, powered by sort of all the electricity that's produced every day right now for a few minutes to give a spacecraft a push with photons. The thing, everybody, your limit with a rocket science, you can't go any faster than the exhaust velocity of the fuel. But with a photon pushed spacecraft, your velocity is the speed of light. So it's quite high, but it's very gratifying whenever they produce images for promotion or fundraising or raising awareness of their spacecraft, they use images of LightSail, because LightSail really is an elegant design that's a product of decades of thinking about it. You know, I say all the time, I read Lou Friedman's book around about 1985, and we're doing it pretty much Lou's way, and it's exciting. It's just cool. Come on. It's a very romantic thing. It goes all the way back. As we say, when you want to explore the solar system, between here and Jupiter, between here and Mars, cheapest way to do it is with a solar sail, just practically. So you all have contributed a great deal to this.
Jennifer, you want to add anything to this?
I don't know if I have that much more I can say, other than that I think that the dream of interstellar flight is compelling. And I think that the concept of always pushing toward these interstellar precursors is a really valuable use of our time and energy as a species to continue to push forward. And indeed, it's almost unfathomable to think about actually getting to the point where humans can achieve this kind of travel. But we know we're never going to do it if we don't start trying. So if we don't start taking these baby steps, and I count LightSail as one of those baby steps.
Hear, hear. All right, Bruce, here is a much more literally down-to-earth question from Stephen Koski. In the future, will the LS-2 orbit take it over the U.S. Northeast?
Nope. Sorry. We're bound within the roughly 24 north to 24 south latitude band. And again, that's something we, as a secondary payload or tertiary payload, not something we chose, but something we adapted to on a rocket launch that we could get. So sorry.
But with LightSail 1,
Yes.
I was in New York City and I saw it. It was a heck of a thing. It was it's really something. Tiny, tiny dot. But because it's so shiny, if you're down in the tropics, you can see it. It's just amazing. And Carl Sagan talked about this all the time, that if you knew where to look, you would see it because it's so reflective.
We're getting a bunch of questions from people asking about, could we scale this up? LightSail, pretty small, obviously. Could we make it really, really big? In fact, one nice way to put this came from Thomas Shanley. Can we make the next one brighter, easier to see, hard to miss? He was able to see it a couple of times with binoculars, but it took planning and care. And he just thinks that everybody ought to be able to look up and see a big sail in the sky. So is this scalable?
Go with Dave on that.
Okay.
Dave?
Oh, sorry, Bill.
Yeah, just real quick, and so there is actually a mission that's being considered right now by NASA that's called Solar Cruiser, and one of our friends, Les Johnson from Marshall Space Flight Center, is leading up this mission proposal, which is in what's called a phase 2, basically the second cycle of being selected, and this is a 1,200 square meter solar sail. LightSail is 32 square meters, just for reference. And so scaling it up to 1,200 square meters would be just amazing. And that mission's going to go to the Sun-Earth L1 libration point. So that's a point where basically it maintains the same position in between the Sun and the Earth that could be used for solar storm monitoring. So that mission, if it's selected, is going to fly within the next decade. And that would be a huge step forward in terms of solar sailing technology.
Bill.
Well, just like a reminder, there are a couple missions that the solar sail is ideal for, and that's one of them, where you'd station keep. You would remain, there's three things going on. The Earth and the Moon are going around the Sun, and so is the spacecraft, and the Sun's gravity is pulling in, the Earth's gravity is pulling out. So it's really an ideal use of a solar sail. Then for hovering above either the North or South Pole, there's certain orbital configurations where a solar sail is ideal. You would monitor climate or weather or what have you. And then looking for asteroids. There's potential for putting spacecraft at certain places along an orbit inferior to the Earth, closer to Venus than the Earth, and looking for asteroids by looking out. So these are practical things that I feel that you, all supporters of the LightSail project, have enabled for the future. You know, the longest journey starts with but a single step, and this is a big part of it.
Here is one from Thomas Shanley, which never would have occurred to me, but it's kind of charming. Did you consult with any traditional ocean or body of water sailors as you figured out maybe how to control a sail driven by light? Bruce?
Well, I did teach windsurfing at one point. Does that count? Okay.
Why not?
Little known Bruce facts. I did not. Maybe others did, but I know Lou Friedman, who has originated this program at the Planetary Society, has been tied into sailing as well. Anyone else have a good answer for that?
I want to go to Bill because Bill, I know you're fascinated by seafaring travel. You've even written some things about it, but I mean, master and commander. I mean, do you see the romantic, there's that word again, connection between that, sailing the seas, and sailing the sky?
So, Matt, what am I supposed to say? No? Yes, of course. Yes, my goodness. It's identical. This is part of the amazing charm that goes back to Johann Kepler. Is the principles are the same. You tack into the wind, you rotate to get a push from the wind. Now, this is not the solar wind, I remind you, it's photons, but the principles are the same. And so there's a center of pressure in sailboats, a center of effort, there's a center of mass. The solar sail spacecraft has all those things. And I spent a lot of time, with fluid mechanics, is my old business, and control systems. And so the solar sail is just my thing, man. It's just this beautiful combination of the same physics. And, as the old saying goes, they say everything happens for a reason. Well, that reason is usually physics. And physics is the study of energy and motion. And that's what rocket science is. That's when you want to get spacecraft in orbit or spacecraft between planets. It's understanding energy and motion. I mean, we're all here because we understand it. And by that, I mean, we're able to raise enough food to feed everybody in the world and so on because we understand the science. It gets me every time I stop and think about it.
Here's another more practical one for Dave. Maybe you can tackle this from Gerald Reichschmeid. I hope I have that right. And you did kind of touch on this, but what is the biggest issue with getting those 90-degree turns just right, closest to the ideal? And he even throws out some guesses here. He says, I assume the sail's flexibility adds to the inaccuracy, but what's the bottleneck to not being able to adjust this at high frequency and counteract this?
Well, there are lots of different challenges. The first thing is you need to know, your spacecraft needs to know what its orientation is in order to know what direction it needs to turn to. And we've got, this is a low-cost spacecraft. You can spend $30,000 on a sun sensor. We're flying really automotive class sun sensors on this spacecraft. So we've got a set of sun sensors. We've got a couple of magnetometers that are measuring the Earth's magnetic field direction. And we use those sensors to figure out what orientation the spacecraft's in. Then in terms of actually turning it to the desired orientation, we use this momentum wheel. And the problem with that is it can reach its speed limit, it can saturate. We've also got torque rods that we can, put an electrical current through that generates a magnetic field to interact with the Earth's magnetic field. That also helps to turn the spacecraft, but those are limited in terms of how much current you can run through them. So, a number of different challenges, and Gerald also mentioned the flexibility of the overall system. And yeah, these booms are flexible. And in fact, Marshall Space Flight Center has shown that these alloy track booms will have thermal distortion. They will bend to, non-linear shapes due to the sun acting on it. So that's one reason that NeoScout, when they fly in a couple of years, they're actually putting the booms and keeping them in shade behind the sail relative to the sun so that they don't run into those thermal problems. So we have to deal with all of those things, and those are all challenges in terms of the solar sailing performance.
So I wanted to just jump in. Bruce, don't you have an example of the boom behind you?
Yes, let me get my prop.
I just thought it would be interesting to show that. Sorry.
1 second.
But
There it
it's
is.
easy then to see how very flexible they are. They're sturdy and flexible.
Yes, so this is the same booms. And so it's, let's see if, no,
Mhm.
not going to happen. It's like two tape measures that have been welded together at a point and therefore doesn't collapse easily like a tape measure does. And it's made of this groovy chromium alloy called alloy that has some nice properties.
So
And
Bend it.
go ahead.
that analogy to a tape measure, except one that goes outward instead of pulling inward, that I've heard you and Bill make, that's not bad for describing deployment?
Well, we'll see if Dave agrees with us. That's the real thing.
Yeah, that's a good analogy, and it's like two tape measures that are welded together, actually.
Yeah.
Let's get to another question, different direction here, literally. How many grams of pressure does the sunlight exert on average at 90 degrees perpendicular to the sun's rays? And that's from Dana Marshall. Now, perpendicular, does she mean when you're edge on to the sun, I assume? But I know you've got a figure for when you're full on to the sun, right? Bill, you talk about this sometimes, the pressure of the light.
Yeah.
First of all,
I think she means when you're getting a full push. I mean,
Okay.
if the thing were paper, it is much thinner than paper.
Yeah.
You get very, very little, but it's 9 micronewtons per square meter. So you get 32 square meters. You're talking about millionths of a newton. And the old saying, an apple weighs about a newton. And so it's the weight of a pretty good sized insect in the middle of a boxing ring. It's not very much oomph. But the thing is, it's day and night. Oh, wait, there's no night. You're in space. And so it's every 100 minutes, every 50 minutes, all the time. And that's the key to this. That's also, if you like to think about these things, that's the key to ion propulsion that's used in a lot of spacecraft, is that it's a very small push, but it goes on all the time. And so the small push adds up because there's nothing to stop you. And for those of you who are into it, grams, is a measure of mass, but we like to go into newtons, which is the measure of force. So it's a very small, a box of butter. That's you're getting in. I mean, a stick of butter. A stick of butter. That's like a newton.
Hey, Matt, one other answer for that. There's a number that solar sailors talk about, which is characteristic acceleration. And that's what acceleration you'll get at 1 AU, at Earth's distance from the sun. And what LightSail is giving us is 5.8 times 10 to the minus 2, so 0.058 millimeters per second squared. That's our characteristic acceleration. And that's the most agile, most accelerating solar sail that's been flown to date, but we will be beaten out by NeoScout when it launches.
There are so many just messages of congratulations and expressions of gratitude for everything that has been accomplished with this mission so far. As we approach half past the hour, we probably need to start wrapping up a little bit. But as we get ready to do that, I mean, the question that I have for you before we get to that toast is, what can everyone do to continue to follow the mission? Bruce, you've already talked about the website. And we've talked a little bit about where the society is going next. Jennifer, do you have further suggestions for people who want to keep track of this and everything else we're up to?
Well, you can sign up for our newsletter if you haven't done that already. So we have a weekly newsletter called the Downlink. It gives you bite-sized pieces of space news, things you can do, ways to get involved. Fun read, easy read, comes to you every Friday morning. So I would say think about adding that into your space mix every week. It's free, it's just a newsletter.
And it's great. It's just packed with great stuff, images and headlines, and it's great fun. I rely on it for the opening of Planetary Radio now to pick up some space headlines. So a lot of fun there. And is that live?
Mm-hmm. Yes.
Okay. We are out over the South Atlantic? Oh no,
Yeah.
that's the Indian Ocean. My goodness,
Yes.
we've been talking a long time, haven't we?
We've gone all the way around. We've gone all the way around to get back to
And-
there.
And
And I
LightSail
also
is
want to
past.
mention our friend Liam and his LightSail Above as well. So
Oh,
I
yes.
know, yeah, I know, Bill, that you're a big fan of the LightSail
Yes, I
Above.
am.
Yeah.
And yeah, it was Liam who tipped me off that we would actually, as we were speaking, it would be passing over at least Baja today. And so that's a great tool, and you can track the International Space Station with that tool as well.
So
Well,
what it does is it lights up and gives you all kinds of notice that it will be headed over you at any given time. So it's a fun little Raspberry Pi computer to have in your home, LightSail Above or ISS Above.
yeah. I will add that we have lots of other resources available. You mentioned the newsletter, the downlink, of course, all of our social media channels, the website, planetary.org, and a brand new issue of the Planetary Report, the June solstice issue of the Planetary Report, released just days ago. I have my paper copy. Bill is showing you his. The paper copy, of course, goes to our members, planetary.org/membership, but you can get the digital version now. It is open to everybody because that's what we're about, is empowering the world's citizens. It's great if you want to be a member and help us do that, but we're here for everybody. Having said that, Bill, I have a glass here. Would you lead us in a toast?
So everyone, there's a lot going on in the world right now. There's a lot of troubles. But as I've said for many years, space exploration brings out the best in us. Space exploration is where we solve problems that have never been solved before. Space exploration is what brings people together to use our intellect and treasure to help us all understand the cosmos in new ways. So with all the things that are going on with us in the world right now, I want to thank all of you for your support, because this spacecraft, and I hope the society writ large, is helping to maintain our view of the cosmos and our place within it so that we remain optimistic. As has been said many times, if you couldn't pick where on the Earth's surface you were going to be born, but you could pick when, this is the time you'd want to be born, because strange as it may seem, things are better now for more people in the world than ever before in human history. And space exploration and our understanding of the cosmos is part of that better future. It's part of us working together. We're realizing that we are all one species on one planet, and working together, as I'm so fond of saying, to continue to explore space, we can, dare I say it, change the world. Here's to you. This is iced tea, which I drink this time of day. Thank you all so much. In a LightSail glass, I hope a few of you who are supportive of LightSail were able to get a set. They work perfectly, but I assure you, they only work this well in a gravity field. You've got to be on the surface of the planet.
Well, Bill, I've got the sun here, so maybe you can just come on, edge on.
Thank you, Bill. That's Bill Nye. He's the science and planetary guy, the CEO of the Planetary Society. I want to also thank our Chief Operating Officer, Jennifer Vaughn, Chief Scientist and LightSail Program Manager, Bruce Betts, and LightSail Project Manager, Dave Spencer. Best of success to you, Dave, as we attempt that other great dream of Mars sample return. I forgot to ask you, what is your new job?
Oh, thank you. So I've just rejoined JPL as the Mission System Manager for Mars Sample Return. We're going to bring back scientifically selected samples from the surface and subsurface of Mars, bring them back to Earth. Hopefully in 2031, they'll crash land in Utah.
A holy grail of Mars robotic exploration. Thank you, Dave.
I was going to say, just
Jennifer?
like solar sailing, the idea of Mars sample return dates back to the very beginning of the organization as well. This is something that the organization has been fighting for and dreaming about. So make it happen, Dave.
Thank you.
All right, everybody. Thank you for joining us today, for your membership, for your support. I'm Mat Kaplan. We'll wish you smooth sailing on your own. And we'll see you out there on the final frontier. And we've got some neat slides to leave you with here as we shut down. I hope you'll enjoy this little video from our ace video producer, Merk Boyan.